Our very last section in chapter 4 is 4.9, antiderivatives. Gonna give us, kind of set the tone, give us a preview of what to expect with integral calculus. Let's check it out. Antiderivatives, what do we mean? A lot of times students see that and they like to be cute and say, you know, I'm antiderivatives. That's not what we mean. The idea is we're working backwards. F prime of x equals, let's go with this example. What if we're given f prime of x equals 3x squared? And the question is, what was the original function f of x? Okay, well, right, if the derivative is 3x squared, you might say, hey, well, then the original function must have been x to the third. Makes sense, right? That would be true. That derivative is 3x squared, but not so fast. Couldn't the original function have also been maybe x to the third plus 1? That derivative would still be 3x squared. And we realize, oh, wow, we know it's an x to the third, but then any number could be added or subtracted off the end. You know, what about x to the third minus 12, you know, something, any of these would give that same derivative. So what we're going to do, say, okay, because we don't know what constant was being added or subtracted off the end, we're going to use this. We're going to say f of x is equal to x to the third plus c. And that c represents a constant. A little bit more precise, we're going to call it an arbitrary constant. Arbitrary meaning it is a constant, so it's fixed, but that number could take on many different values, let's say. We say plus c, but we do allow the c to possibly represent a negative number. If we were going to think of something like minus 12, then c would be negative 12. Okay, let's now define an antiderivative. When we do this, we're going to kind of introduce a little bit different notation. We're going to call the antiderivative capital F of x. And you'll notice that we're saying capital F of x is an antiderivative of lowercase f of x. And that would be true if the derivative of the capital F of x is equal to the lowercase, the little f of x. So what's different here? We're not thinking of what we're starting with as f prime of x and then going back to f of x. We're saying, think of what you're starting with simply as f of x, right? So we're not thinking of it as being a derivative necessarily. We're just thinking of it as being a function. But then we find the antiderivative of it. What would we take the derivative of to produce that function? And so it's antiderivative. Well, there's no primes anymore. So what we're going to do is call it capital F of x. And this seems kind of strange and confusing. Why not just use the primes? That's what we've been using all along. We're going to, obviously use this notation as we do examples, and hopefully it will become more clear. Notice that in that definition, we say capital F of x is an antiderivative. Technically, there are infinitely many antiderivatives for any function because of that plus c, and the c could take on any constant value that we like. So here's what we're going to do instead. We're also going to define the general antiderivative. The general antiderivative is where we use just the plus c. So we'll say capital F of x plus c. In our example, that capital F of x would have been the simplest one, the x cubed, right? And then we put the plus c on the end. Okay, let's practice this. Got a bunch of examples right here, 5 of them. Finding the general antiderivative. We'll do mostly polynomials, but you notice we're going to throw in e to the x, and we've got that big fraction there in part E. Okay, let me switch over. Here we go. Example, find the general antiderivative. And part A, f of x equals 40 x to the third. Okay, so again, it's like we're thinking of it, hey, there's just a function doing its thing, you know, but what would the antiderivative be? And that we call capital F of x. Okay, so working backwards definitely takes some practice. Let's think here. If 40x cubed, if we are seeing an x cubed as a derivative, what must that have come from? What power of x? Well, it must have come from x to the fourth. Okay. Then if we were to perform the derivative, the 4 would multiply down and the result would be 40. So what did it multiply with? Well, had to be 10, right? 10x to the fourth. And then we put the plus c because anything could have been added or subtracted off the end. There's our general antiderivative. Capital F of x equals 10x to the fourth plus c. There we go. All right. Part B, how about this? Little f of x equals x to the seventh plus 3e to the x. Now the way derivatives work, right? If we're adding, we can do them separately. So we'll start with x to the seventh, capital F of x. Let's think here, x to the seventh. It must have come from x to the eighth. But then in a derivative, this 8 would multiply down, yet I don't see a number in front of x to the seventh. So what's happening there? Well, whatever it multiplied with, it canceled out and we just got the 1. So it must be 1/8 x to the eighth. So when that 8 multiplies, it cancels out. Okay, very nice. Plus, hey, what about 3e to the x? Well, the derivative of e to the x would give e to the x, and the 3 would carry along. So that would just be 3e to the x again, because this derivative would result in that. And then, of course, plus c. And we got it. Okay, very nice. Now we've got a full-blown polynomial, x to the ninth plus 2x to the sixth minus 1/2 x squared plus 1. Let's see how we do. See if we've kind of gotten our feet under us with these. Capital F of x. What would happen with x to the ninth, right? Kind of like x to the seventh. It would have come from x to the 10th, but then the 10 would have to multiply down and cancel out. 1/10 x to the 10. Give our x to the ninth, all right, and then plus, let's see, 2x to the sixth. Must have been x to the seventh. How is this going to work? What would the 7 multiply with to give a 2? You think, well, the 7's got to cancel out, so let's just say 2/7. And that'll do it. Kind of one of the themes, one of the patterns here in working backwards, whenever you're working with the power of x, think about what that power would be in the antiderivative, and then you know whatever number's out in front, you got to divide by that, right? So it would have been a 10, so it's like take the 1, divide by 10. It would have been a 7, so 2 divided by 7, right? And same idea here, right? The 40 divided by the 4. You can work backwards. Ooh, what would that mean for 1/2 x squared? Well, it would have been x to the third. So we'll take the 1/2 and divide it by 3. That would give 1/6. And yeah, the 3 multiplies down, and it would reduce and give you the 1/2. Good. Plus 1. What's the antiderivative of 1? What do you take the derivative of to produce this? Well, it's just x plus x, and then plus c on the end. Don't forget the plus c. There it is. Okay, moving along. So far, so good. D. Mixing it up again. F of x equals square root x plus 1 over x. When I see square root x, I would prefer to think of that as x to the 1/2. So let me do that. Let's think here. X to the 1/2. Well, if I add 1 to the exponent, that's going to be 3 over 2. Okay. And then what happens in front, right? Oh man, 3 over 2. It's got to cancel out when we multiply. Well, I could think of like 1 divided by 3 over 2, or I could think of the reciprocal of 3 over 2. It would multiply by 2/3. That would cancel both the 3 and the 2 and leave me with x to the 1/2. Okay, plus 1 over x. Hey, what's the antiderivative of 1 over x? And well, what do you take the derivative of to get this? Natural log of x. Okay, one thing here. When we do an antiderivative, we got to write the natural log of the absolute value of x. And of course, let me put on the plus c, but let me explain this. There's our answer. Why do we need an absolute value of x? Kind of a subtle point. So it comes back to the domain of the natural log. Turns out we cannot perform a natural log of a negative number or 0. You can only take the natural log of a positive number. Like, okay, so no big deal. So what? Well, think about where it came from, right? 1 over x, we would allow negative x values. We would not allow 0, but we would allow negatives. That would be fine. But if we allow a negative there, and we think, okay, antiderivative, whatever x values are okay here need to be okay here. So if we need to allow negative numbers, we'd say, well, we can put a negative number in there so long as we first perform an absolute value and then apply the natural log to it. So we end up doing a natural log of a positive number. So we can put negative x values into this where we could not have put a negative x value into natural log of x. So kind of the explanation here, this must match the domain of 1 over x. And that domain is negative infinity to 0, union 0 to infinity. These numbers would have been fine in natural log x, but these negative numbers, right, we got to perform that absolute value first. Okay. Part E, we got one more in this list of examples. F of x equals x to the 5th plus 2x squared minus 1 over x cubed. All right, well, you look at that, and maybe your first reaction is like, oh man, I see a big fraction, it's like quotient rule. But we're working backwards. So is there like a backwards quotient rule? No, don't even think about, like, that would be impossible. A quotient rule in reverse. It's actually, we're gonna need a different approach for this. We need to rewrite it kind of like when we rewrote the square root as x to the 1/2. We can do something kind of similar here. What we'll do, since we're dividing by x to the 3rd, we'll divide each one of these terms in the numerator separately. Let me maybe put it out to the side. So this will be x to the 5th over x cubed plus 2x squared over x cubed minus 1 over x cubed. Okay. And then reducing each of these, we'd have f of x still is x squared. Here, we'd get x's to cancel. And then finally, you know what? This one, I'm going to write that as minus x to the negative 3. Okay. So for the antiderivative, f of x, capital F of x, x squared would have come from 1/3 x to the third. 2 over x would have been 2 natural log absolute value x. And then negative x to the negative 3. Let's see. If we add 1, that's x to the negative 2. Be careful with your negative exponents, right? Adding 1. And then this negative 2, we need to multiply by something to end up with just a negative here. Well, I think it's got to have to be positive 1/2. It's like we're dividing by negative 2. So that would multiply and we just get a negative. There we go, plus c. And we got it. Okay, very nice. We're going to stop here. We got one more example to chat about in the next video.